So a conditional statement is any statement that can be written in if-then form. So you might recognize these because if you write like a hypothesis for a science project or something, you would write if blah blah blah, then blah blah blah. So it's called a conditional because the truth value of whether the statement is true or not depends on whether the hypothesis is true and then whether the conclusion is true. So an example of a conditional statement that is true is if you are a 10th grader in AGS, then your English teacher is Mrs. Webster. So all of you in this class are 10th graders in AGS, and all of you have Mrs. Webster for English. So these statements, a lot of the time we write these in symbolic form. So we might write the hypothesis. So the hypothesis is the phrase that comes after the word if. So the thing that we want to say is true. And then the conclusion is what follows the hypothesis. So sometimes we just write this as P and then an arrow and Q. So this would be read if P then Q, or P implies Q. And in this Venn diagram here we have P is in the inner circle because P is true. So whenever P is true, Q is also true. Notice we also have this part outside here, so Q can be true while P is false. So in this first part, so identify the hypothesis and conclusion of each statement. So remember, the hypothesis is what comes right after the word if. So if you want good grades, then you should attend tutorials regularly. So the hypothesis would be you want good grades. And the conclusion would be you should attend tutorials regularly. Hint, hint. All right, and then a more math-related example. So if two angles form a linear pair, then their angle measures add up to 180. So our hypothesis would be two angles form a linear pair, and the conclusion is their measures add up to 180. So the hypothesis of a conditional statement can be true or false. And then the truth value, so this just means whether a statement is true or not. Its truth value of the entire statement depends on both the hypothesis and the conclusion. So let's consider the following statement. If Tom finishes his homework, then he will clean his room. So we have here the four possible cases of each statement. So the hypothesis could be true while the conclusion is true, or we could have the hypothesis is true and the conclusion is false. And then here we have both the cases where the hypothesis is false and the conclusion is true, or the hypothesis could be false and the conclusion could be false. So if Tom finishes homework and he cleans his room, then the conditional is true. Right? So that means Tom fulfilled his promise. He said he was going to do his homework and then he was going to clean his room, and he did. So here, Tom finishes his homework, but the conclusion ends up being false. He finishes his homework, but he does not clean his room. So here, the whole statement is false. Tom's a dirty liar, and he didn't clean his room. Right? Now here we have the two cases where the hypothesis is false. So the statement, original statement is, if Tom finishes his homework, then he will clean his room. If Tom does not finish his homework, he'll probably fail. But also, we can't say anything about whether the original statement is true or not because its hypothesis was not true. So we cannot evaluate the conditional because it's neither true nor false because the hypothesis was not true. So we can only say this statement is true or false. We can only make a truth claim about this statement if Tom finishes his homework. If Tom doesn't finish his homework, then we don't know if he would have cleaned his room, right? So we can't say the whole statement is true or false. So we have these related conditionals are other ways we can arrange the hypothesis and conclusion in a statement. So here we just have the original conditional. So if P, then Q, right? The converse is when we exchange the hypothesis and the conclusion. So we switch Q and P. So this now says if Q, then P. So look at the examples here. The example of an original conditional is if angle A measures 35, then angle A is an acute angle. And that's true, right? This one's true, because 35 is less than 90. This says if angle A is an acute angle, then measure of angle A is 35. And that's not necessarily true, right? Angle A could be acute, but the angle could measure 39 or 40 or 52, right? So false. So now we have the inverse. The inverse is formed by, we go to the original, but we negate both of them. So this symbol, the squiggly, it's the logical symbol for not. So this says not P implies not Q. So if angle A is not 35, then angle A is not an acute angle. But this is also false, because angle A could be 36, but it's still an acute angle, right? And then we have the contrapositive. And this is when it's the combination of the converse and the inverse. So we switch them and we negate them. So we have if angle A is not acute, then measure of angle A is not 35. And this is true, because if angle A were 35, then it would be acute. So if it's not acute, then 35 is one of the many measures that angle A could not be. So an important takeaway here is that a conditional and its contrapositive are logically equivalent. So they will always have the same truth value. So if a conditional is true, then its contrapositive is true. We could even write that. That's a conditional about conditionals. Then its contrapositive is true. Contrapositive. And similarly, the converse and inverse are always logically equivalent. So if a converse is true, then the inverse is true. However, if a conditional is true, its converse is not necessarily true. So like we saw here, this conditional statement, if angle A is acute, then, or if the measure of angle A is 35, then angle A is acute. When we looked at the converse and inverse, they were both false. Now sometimes they can be true, and we'll see that in a second. So write the converse, inverse, and contrapositive of each conditional. So we have if a shape is a triangle, then its angle measures add up to 180. So the converse is we're gonna flip the hypothesis with the conclusion. So now we have if a shape's angles add up to 180, then it is a triangle. This would be the converse. The inverse of the statement is we're going to take the original statement and put not on both of the hypothesis and the conclusion. So if a shape is not a triangle, then its angles do not add up to 180. And the contrapositive is where we're going to switch it and we're going to negate it. So if a shape's angles do not add up to 180, then it is not a triangle. So this one, we said, so the original statement was if a shape is a triangle, then its angles add up to 180. So the converse, I swapped the statements. I said if the angles add up to 180, then it's a triangle. So originally triangle was before the comma, now it's after the comma. Inverse, I took the original statement and I put a not in both of the clauses. So now we have if a shape is not a triangle, then its angles do not add up to 180. And the contrapositive is when you negate and switch. So shape's angles do not add up to 180, then it is not a triangle. And in this one, we could actually, all four of these statements end up being true. So if a shape's angles add up to 180, then that shape has to be a triangle. And if a shape is not a triangle, then its angles will not add up to 180. And the contrapositive we know is true because the conditional is true. And a less math-related example. So if Mr. Trenfield, that's me, if I don't drink coffee, then I get a headache. That's very true. The converse of this statement would be if Mr. Trenfield has a headache, then he didn't drink coffee. And this would be the converse. So if Mr. Trenfield has a headache, then he didn't drink coffee. That would be the converse of that statement. And that's, I mean, it could be true sometimes. If I didn't drink my coffee, I would have a headache, but there's also many other things in life that can give me a headache, not just lack of coffee. Inverse of this statement. So if Mr. Trenfield, so this original statement already says does not. So if I'm negating that statement, then my statement is if Mr. Trenfield does drink coffee, then he will not have a headache. And that's true most of the time, but like I said earlier, there's lots of things in life that can give me headaches. So some days are just rough and I drink my coffee, but I still have a headache, you know. Life's hard sometimes, you know. And the contrapositive. So if contrapositive is when I negate and switch. So if Mr. Trenfield does not have a headache, then he did drink coffee. And again, that's true. Because I always get a headache when I don't drink coffee. So if I don't have a headache, then I must have had my coffee. So, write the converse of each statement and then state whether the converse is true. This is a really important part of math. So we have a lot of theorems in math that are true in one direction, but then their converses are not true. So if x is greater than 1, then x squared is greater than 1. So the converse would be if x squared is greater than 1, then x is greater than 1. So now we have this statement here, and we want to know if the converse is true. The original is true because if we take a number that's greater than 1, like 2 or 3 or 5 or 120, and we square it, we're going to get another number that's bigger than 1. But the converse, if x squared is greater than 1, then x is greater than 1. This is false. Because if I take a number like -2 and I square it, that equals +4. Whoa. But -2 is not greater than 1. -2 is less than 1. So that statement is false. Number 6, if a number is prime, then its only factors are 1 and itself. So the converse of this statement would be if a number's only factors are 1 and itself, then the number is prime. And this statement is true, because that's still the same definition of a prime number, right? A prime number is any number whose only factors are 1 and itself. So there can't be any numbers that have only factors of 1. Oh, I just thought of something. We could kind of say this is false, but maybe not. So if a number's factors are 1 in itself, then the number is prime. Yeah, we'll say this is true because 1 and itself would imply that 1 cannot be a factor. So if a triangle is a right triangle, then a squared plus b squared equals c squared, where a and b are the lengths of the hypotenuse, are the lengths of the legs, and c is the length of the hypotenuse. So this is the Pythagorean theorem, of course. And it's actually, so the converse of the Pythagorean theorem is if, converse would be if we have a triangle where a squared plus b squared equals c squared, then it is a right triangle. And this statement is true. And this is a really important mathematical fact. We've used this in class because we've used Pythagorean theorem both to solve for missing sides of right triangles and then also to verify whether a given triangle is a right triangle. So this is a really important true statement, where an example of where the conditional and the converse are both true. All right, so you have an assignment about conditionals and conditional statements, and if you finish that, then you get to work on your idea books. So do work.